Hi folks, I hope that you can see and hear me okay. Uh, Welcome to my basement from wherever you're watching. Um, so let me know in the live chat that you're able to see and hear me okay. Um, so it looks like a lot of people are watching from campus. Some people are watching from their beds at home. Um, Some of you are in an airport, maybe you're in an airplane using airplane Wi Fi. Glad you're here in any case. Um, so, our main purpose here is to make sure that we don't forget about calculus for a week and a half. Um, so, if you have questions as we go along, feel free to either post them in the live chat. I'll try to keep an eye on that. Um, you can also send me questions or comments by text as usual, and I'll be keeping an eye on that as well. Uh, okay, so a little bit about the calendar for the rest of the course here. We're going to continue with section 5.4 today on indefinite integrals and net change. You did some examples yesterday in discussion in that section. We'll continue that discussion today. On Monday, we'll begin the last section of Chapter 5 on substitution. And essentially, that's the chain rule in reverse. Chain rule for definite integrals. Um, so the three big remaining assessments are next Thursday will be your 10th and final quiz covering section 5.3 on the fundamental theorem of calculus and section 5.4 which is the section we're on now. Exam 3 is the following Thursday. It will cover chapter 5 and sections 1 and 2 of chapter 6. After that, there's two more sections of chapter 6 we'll cover before the end of the course, and then the final exam is from 12 to 3 on Friday, December 15th. The locations won't be your normal discussion room, but we'll post those locations soon. As I mentioned in lecture on Monday, I'll give you a quiz bonus for attending today, and I'll give you details about how to cash that in later in the time here. Let me just go to the Moodle page for the course real quick so you know where some resources are. So here's the Moodle site for the course. There's the calendar with those three assessments remaining that I mentioned. You'll see there that in the sample exams folder, I've posted a practice exam and some extra practice that you can use to get ready for exam 3. And then let me also mention that there's a new link here to the Math 1271 library course reserves, and you can go there, go under the tab labeled course reserves, and there's a bunch of old final exams from our course Math 1271. But for the meantime, focus on getting ready for quiz 10 and exam 3, and by doing so you'll be preparing for the final exam as well. Okay, so back to the slides, and we're talking about section 5.4, net change. basically this is attaching applications or real world meaning to the fundamental theorem of calculus. You might think of the integrand f as a velocity function, for example, and then its antiderivative, capital F, is the position function of the object. And then the fundamental theorem of calculus is basically saying that the integral of the velocity function is the total net change in the position of the object on that interval on which you are integrating. And so that total displacement is the definite integral of the velocity function, whereas total distance traveled is the integral of the absolute value of the velocity function. And so think of the velocity as a signed quantity. Maybe a positive velocity means that the particle is moving to the right, and a negative velocity means that the particle is moving to the left, whereas the absolute value of the velocity is the speed, and the integral of the speed will tell us the total distance that the particle has traveled, whether it's moving to the right or to the left. All right, so let's do some examples similar to those that you did during the discussion yesterday. First, let's suppose that a particle moves along the line to the right when the velocity is positive, and it moves to the left when the velocity is negative. And let's assume that this particle has velocity v of t equals cosine t in meters per second from time t equals 0 to time t equals 2 pi, which is about 6 seconds and change after we began. So let's find first the total displacement of the particle, and then let's find the total distance traveled of that particle on this time interval of 2 pi seconds. First, let's take a look at a graph of the cosine. It's in blue, and we're going to first find the total, the displacement of the particle. And so notice that the cosine is telling us the velocity of the particle. It's positive on the interval 0 to pi over 2, which means that it's moving to the right. Then the cosine is negative on the interval pi over 2 to 3 pi over 2, which means that the particle is moving back to the left. I'm pointing to the left and it looks to you like I'm pointing to the right, but the particle is moving to the left because the velocity is negative. And then again on the interval 3 pi over 2 to 2 pi, the velocity is positive, and hence the particle is moving back again to the right. All right, so let's calculate. Let's find the total displacement of the particle. And so we just said that the total displacement is equal to the integral of the velocity on the interval. So we're finding the integral from 0 to 2 pi of this velocity function cosine of t. And now, thank goodness, we don't have to evaluate some limit. We can apply the fundamental theorem of calculus. And so we need to know an antiderivative for the cosine. We know that the derivative of the sine is the cosine. And so let's use our fundamental theorem of calculus notation and say that this integral is equal to the difference of the evaluation of sine t at 2 pi and at 0. All right. So I want to make clear here that that equality is by the second part of the fundamental theorem of calculus. And so the sine of 2 pi is 0. And then we subtract the sine of 0, which is also 0. So this integral is 0. The total displacement being 0 means that a particle ends up where it started. And so that makes sense informally if we go back to the graph in blue of the cosine. What's happening here is that for the first pi over 2, it moves to the right. Between pi over 2 and pi, it moves back to its starting location. Between pi and 3 pi over 2, the particle moves to the left of where it started. And then between 3 pi over 2 and 2 pi, the particle moves back to the right and ends up where it began at t equals 0. All right, so that's total displacement. There's no displacement. Move to the right, move back to the left, and then move to the right to the initial starting location. Now let's find total distance traveled. Total distance traveled is the integral of the speed, which is the integral of the absolute value of the velocity function. And so let's first write that this is equal to the integral from 0 to 2 pi of the absolute value of, not sine, cosine of t integrated with respect to t. All right, and so now we want to think of this as a sort of piecewise defined function, because the absolute value of cosine of t will be just cosine t when it's positive, but when the cosine of t takes negative values, then its absolute value will be the negative of cosine t. And so if we go back once more to the graph of cosine in blue, you can see now why I've graphed negative cosine in red. We'll want to break up this integral into 3 parts, because that integrand, cosine of absolute value of cosine of t, will be just cosine on the interval 0 to 2 pi. It'll be cosine on the interval from 3 pi over 2 to 2 pi. And then we'll be integrating negative cosine between pi over 2 and 3 pi over 2. All right, in other words, we're going to break up the integral into 3 integrals on 3 subintervals. So let's go back to the calculation. We're going to write this integral as the integral from 0 to pi over 2, where the cosine takes positive values. And so we're just integrating the cosine. And then we're going to add the integral from pi over 2 to 3 pi over 2. And that's the middle interval on which the cosine takes negative values, and hence its absolute value will be negative cosine. And then finally, we integrate over the third subinterval from 3 pi over 2 to 2 pi. And on that subinterval, the cosine takes positive values, and hence the absolute value of cosine t is just cosine t. All right, so we already know that an antiderivative for cosine is sine, and hence an antiderivative for negative cosine is negative sine. And so let's use the fundamental theorem of calculus in each of these three cases. In the first integral, we're evaluating sine t at 0 and pi over 2. In the second case, we're evaluating negative sine t at 3 pi over 2 and pi over 2. And in the third integral, we're evaluating sine t again at 2 pi and 3 pi over 2. All right, and so just to make clear what we're about to write down, if we go back to the previous page, you can see that the three integrals respectively are going to tell us this area, this hump in the middle, that area, and then this area. So it will stand to reason, it'll be a good check for us if we see that the first and the third integral have the same value, and the integral in the middle will have a value that's also positive and double that of the first and third. So let's check that the calculation works out that way. I'll go back and look through the live chat, but I'm noticing Kylie's question here. How would you know to break up the function into those three integrals if you were not given a graph? I guess I would say that if you were more generally given an integral of an absolute value, then you would want to know where the function inside the absolute value took positive values and took negative values, because then that helps you determine whether you're applying that negative sign, and I'll point right to that negative sign. That negative sign right there comes from the fact that we know that the cosine takes negative values on the interval pi over 2 to 3 pi over 2. So let me know, Kylie, if that addresses your concern. So we can look at the graph of the cosine here, or we can just know basic trigonometry facts about the cosine. I'm also noticing Ahmed's question here. Hi, Ahmed. So when you say FTC1, I'm assuming that you're referring to the part of the fundamental theorem of calculus that tells us about the rate of change of that accumulated area function that has the x in the right endpoint of integration. And so the answer here is no, we're not using that part of the fundamental theorem to evaluate. Rather, we're using the second part where we write capital F of A minus capital capital F of B minus capital F of A. And we've done that for 3 different integrals here on the last line that we've written so far. So I hope, Ahmed, that helps you see the distinction between the 2 parts of the fundamental theorem. All right, so let's write down the result of our calculation here. All right, so the sine of pi over 2 is 1, and the sine of 0 is 0. So that first hump has value 1. And then in the middle, we're evaluating negative sine t at 3 pi over 2. Sine of 3 pi over 2 is negative 1, and the negative of that is positive 1. And then we subtract negative sine pi over 2. And so we're subtracting negative 1. And so the value of that second integral will be 2, which is double the value of the first integral as we were hoping. And then finally, we're evaluating sine at 2 pi and 3 pi over 2. Sine of 2 pi is 0. And then we subtract the sine of 3 pi over 2, which is negative 1. And so what you see we have here is 1 plus 2 plus 1, which is equal to 4. And so let's make sure we've got units correct here. Back in the original statement of the problem, we were given velocity in meters per second. And so when we integrate the velocity and get a total distance traveled, we're going to get an answer here in meters, 4 meters traveled. Okay? And so what's happening here is the particle moves 1 meter to the right and then moves 2 meters to the left. So it's to the left of where it was originally. And then it moves 1 meter back to the right for a total distance traveled of 4 meters, but a total displacement of 0. All right, so let me pause here. I'll scroll back through the live chat for a second, and feel free to post a question if any of that calculation did not make sense. Okay, it looks like people are able to see and hear me and see the slides. Thanks, Seth. Yes, this is my basement. It sounds like some of you like going to lecture in your bed, in your pajamas. I like being in my basement. We'll see what we can do. All right, so let's move on. Now let's see if you all can do some similar calculations. Hi, Annika from Los Angeles. Glad you're tuning in. I'm going to pretend that it's not 75 degrees Fahrenheit and perfect weather there. Amber, for absolute value, when do you make the value negative or positive? Right. So let me write down first generally what we mean by the absolute value, and then I'll say how that gets implemented in the case of this problem. All right, so I'll write down here in red that the way we define absolute value of x is defined to be just x itself if x is positive or 0, and then we define it to be negative x if x is negative. And so notice that if x itself is negative, then negative x will be a positive quantity. And so if we go back up here to where I made the red arrow, notice how at that line we were identifying, and I hope, Young, that this also addresses your question as well as Amber's. On this second line, we were asking the following question. We're asking, where is the cosine of t positive, and where is the cosine negative? Where does the cosine take positive values, and where does it take negative values? And so whether you know this from general trigonometry understanding, or whether you're looking at a graph as we did on the previous slide, what we observed is that the cosine takes positive values on the interval 0 to pi over 2, and then it dips below the x-axis, or the t-axis here, and takes negative values on the interval pi over 2 to 3 pi over 2. And so this is the crucial part. You see here that we integrate negative cosine t because that's an interval on which the cosine takes negative values, and hence the absolute value adds a factor of -1 in front. And the reason that we're integrating the absolute value of the velocity is because we're calculating the total distance traveled of the particle, not the total displacement of the particle. And so then this third integral here, we're noticing that the cosine takes positive values on the interval 3 pi over 2 to 2 pi. And then that's why the integrand here is simply cosine t again. All right? And so let's try to put this into practice in the next example that I'd like you to spend some time working on there at your desk or in your bed or wherever you're doing your calculations. Let me check in with Young here. So the total distance traveled is only asking where does the function take positive and negative values. So to step back to our two calculations here, if we're finding total distance traveled, we're integrating the absolute value of the velocity function. And in order to integrate that, we have to break up that integral into subintervals on which we can write the velocity function or its negative, depending on whether the velocity function takes positive or negative values on those subintervals. So let's try that again here, except in a place where we're not going to apply the fundamental theorem of calculus, but rather in a place where we're just going to find areas of triangles. Okay, so in this example, we have a particle, and again, positive velocity means move to the right, and negative velocity means move to the left. And I've given you a graph here. Not a formula for it, but just a graph. What I'd like you to calculate first, and post in the live chat, please, the answer that you find. Let's find first the total displacement of this particle from its initial position after 5 seconds from t equals 0 to t equals 5. All right, so I don't need you to get out your ABCD cards. You can just post a number into the live chat, find the total displacement, and notice here that I've drawn some helpful vertical line segments here so that you can recognize the integrals that you're doing as areas of triangles. So take a second there at your seat and carry out this calculation, which is the total displacement, which is the integral of the blue function, the velocity function. All right. B, 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 B. Excellent. We've got a bunch of B's and a bunch of 5's. Let's carry out the calculation there and verify that B is indeed the correct answer. Um, we're finding total we're finding total displacement, which means that we're integrating the velocity function, not the absolute value of the velocity function. And so we're essentially finding areas of triangles. And in this case, we're finding the signed areas. And so on the left, from 0 to 2, we're writing down the area of a triangle that has base 2 and height 5. So that area is 5. All right. The second triangle there between t equals 2 and t equals 3 has base 1, height 5, and so its area is 2.5. On the interval t equals 3 to t equals 4, the velocity is negative, which means that the particle is moving back to the left. And so this triangle has base 1, height -5, you might say. And so its signed area is -2.5. On the interval 4 to 4.5, we've got an area of 1/2 times -5 times 1/2. That's -1.25. And then on the interval on the interval t equals 4.5 to t equals 5, we've got a triangle with area 1/2 times 1/2 times +5. So that signed area is 1.25. And so notice here that the integral that tells us the total displacement will be the sum of all those signed areas. And so notice how the 2.5 here cancels with a -2.5. The -1.25 here cancels with the 1.25 there. And so the value of this total displacement integral is just 5. And let's make sure we know what the units of that quantity are. Here we've been given a velocity in feet per second, and so the total displacement here is 5 feet. And what that means is that the particle is 5 feet to the right of where it started. So the fact that that number is positive means that the particle ends up to the right of where it started. Okie doke. Let me ask you to try one more here. Same particle, same velocity function. Now I'd like you to calculate what the particle's total distance traveled is after 5 seconds. And so again, like we did in example 1, I'm asking you to find the integral from 0 to 5 of now the absolute value of the velocity function. And in this case, we simply break up into subintervals based on whether the graph is above or below the t-axis, and then we treat every negative signed area as a positive quantity. And so great. Okay, Gretchen. I understand. And so Gretchen, I guess I would ask you to go back and draw the analogies between example 1 and these two examples where we find total displacement by integrating the velocity. We find total distance traveled by integrating the absolute value of the velocity, which then requires us to know where the velocity is negative and turn all those function values positive, and the intervals we need to find where the velocity is positive. So I can understand the confusion there. I can also see that many of you are typing D into the live chat. That's great. You have the correct answer here, which is D, 12.5 feet. And let's just take advantage of all the calculations that we've done so far. We know that this first triangle has area 5. The second triangle has area 2.5. This third triangle had signed area negative 2.5, but now of course we're turning that positive, right? Let me see if I can draw that in. We are taking the absolute value of the blue graph, so we're actually integrating under here. We're flipping that part of the graph up. And so we'll say that this area is positive 2.5. This area here is positive 1.25. This area here is positive 1.25. And so the integral at the top has value 5 plus 2.5 plus 2.5 plus 1.25 plus 1.25, and that total sum is 5 plus 5 plus 2.5 equals 12.5. feet. All right. Thanks, Martin, for the dog emoji. Excellent. All right. So, got about 10 minutes here. Let me shift gears and make sure we get to the other main idea of section 5.4 here, which is about indefinite integrals. And really, this is just a matter of notation. An indefinite integral is a family of antiderivatives. So when we write an integral sign with endpoints, with specific left and right numerical endpoints, then the result of calculating that definite integral is a number, whether we evaluate a limit directly or if we apply the second part of the fundamental theorem of calculus. If we write an integral sign without endpoints, then that's simply our notation for the general antiderivative of the integrand function. And so the distinction you want to keep in mind is that the definite integral is a number. That calculation gives us a number, as in the previous examples, but an indefinite integral is a family of functions. And when we write that family of functions, we know we'll have a plus c at the end, because that is our way of reminding ourselves that all of the antiderivatives of a given function are just constants away from each other. So let's use the notation in an example. Okay? So let's contrast the indefinite integral of the sign from the definite integral of the sign on a particular interval. And so when we write the integral of sine x dx, I'd like you to think of the integral sign and the dx simply as two parts of the same symbol. All right? That's just saying, what is the antiderivative of the sine of x integrated with respect to x? And so here, what we write is that the indefinite integral of sine of x is equal to negative cosine x. That's an antiderivative of sine. And then we write plus c to integrate, to indicate that that's the entire family of antiderivatives for sine of x, where c is any real number. On the other hand, for a definite integral, we would evaluate and get a number. And we can use that knowledge from the indefinite integral to apply the fundamental theorem of calculus. And so here, to evaluate, we'd note that negative cosine x is an antiderivative for the sine. And then the fundamental theorem of calculus, part 2, tells us that we can evaluate that antiderivative at pi and at negative pi. And so by the fundamental theorem of calculus, this antiderivative is equal to negative cosine pi, which is equal to 1, minus negative cosine of negative pi, which is also 1. And so that definite integral has value 0. To reiterate, the definite integral is a number. The indefinite integral above, where we don't have limits on the integral sign, is a family of functions. Negative cosine x, negative cosine x plus 12, negative cosine x plus pi squared, all of those. This is a family of functions, a family of antiderivatives. All right. One more example, please. I'll take 5 more minutes of your family time or holiday time. So let's do one more example where we're writing down an antiderivative. All right. So here the integrand is sum of two functions, and each function is a power of x. All right. And so when we calculate, let's first rewrite the integrand as a sum of powers of x. So the square root of x cubed is x to the 3/2, and the cube root of x squared is x to the 2/3. Okay. And we're simply writing down the family of antiderivatives. We're writing down an indefinite integral. And so we're just using the power rule. An antiderivative for a sum of functions is the sum of the two individual antiderivatives. And each one of those we get from the power rule. And so in the first case, an antiderivative is x to the 5/2, one larger power, divided by that power, divided by 5/2, plus an antiderivative for the second function. 2/3 plus 1 is 5/3, and then we divide by 5/3 and add a constant. All right, and so let's rewrite those fractions in the denominator a bit. We can write 2/5 x to the 5/2 plus 3/5 x to the 5/3 plus that constant. That's the family of antiderivatives for that sum of powers of x. All right, so my hope for you is that you have a wonderful break, but that you do not forget entirely about calculus. Try some of the problems. From section 5.4 and also 5.3, because our quiz 10 next Thursday will be over those two sections. So, hi Bernardo, let me repeat your question here. Would it matter if you subtracted the constant? And the answer is no. That would be fine. You could write instead here negative c, and so let's say that your c is in red and mine's in black, and so that represents any real number constant. And so if I had c being, say, 7, then in the way you wrote it, your c corresponding would be -7. And by writing it in either of these two ways, we're accounting for any real number that gets added to form another antiderivative. So no, it would not matter. That would be fine. And if you wrote that on a test, then your grader, your TA, would get a little chuckle out of that and probably draw a little smiley face on your exam. I saw what you did there. Great. All right, Bernardo. Okay, so it's 11 o'clock. Thanks for your patience. Glad you were here. So now let me give you details about what I'd like you to do to get the bonus credit for being here today. So when we calculate your quiz grade, it'll be best 8 quizzes out of 10. And each of those quizzes is worth 20 points. So your quiz score will be out of 160. And so for being here today, I offer 3 points added to your final quiz score. And so, in other words, it's not adding to a particular quiz, it's adding to your final quiz score. And so essentially, it's 3 points added to your worst quiz, up to a maximum of 160 total points. So what I'd like you to do is send email from your UMN email address to my UMN email address, mosher@umn.edu, and make the subject line Math 1271 : present, meaning I was present here. All right. That way, if you send that subject line, then I'll be able to manage all those emails with an email filter. You don't have to put anything in the body of the email, but just send me an email with that subject line, and the TAs and I will make sure that you get those 3 points of credit. And so let's say that you need to send me that email by 11:15, okay? And that will verify to me that you were tuning in here today with all of us by 11:15 a.m. today. All right, so I hope that you found this useful. So Caleb, no worries about the spacing. I'll be looking at the emails pretty much by hand anyway, so don't feel like some computer is going to deny you credit here. So great. I hope that you all have a nice holiday. I hope that you're with family, friends, and loved ones, and I will see you in person, whether it's in your pajamas or in your school clothes, on Monday at 10:10. All right, I'm signing off. Take care.